this module, you will learn about angular displacement, angular velocity, and their relationship with linear velocity and angular acceleration. Consider a rigid body in pure rotational motion about a fixed axis. As you have already studied, each particle of the rotating rigid body executes uniform circular motion. The center of the circular path is on the axis of rotation, and the plane of the circle is perpendicular to the axis of rotation. Observe a particle at P in the rigid body, that is, at a perpendicular distance r from the axis of rotation. Let O be the center of the circular path of the point. While the rigid body is in rotational motion, if the position of the particle is changed from P to Q during a small interval of time, delta t, then the angle POQ is called the angular displacement. In the SI system of units, angular displacement is measured in radian. In fact, when the rigid body is in pure rotational motion, the angular displacement of any of its particles is the same and is equal to the angle through which the rigid body is rotated about the axis of rotation. If the angular displacement of a rigid body is delta theta during a small time interval of delta t, then the average angular velocity of the particle is defined as the ratio of delta theta to delta t. The limit of this ratio as delta t tends to 0 is called instantaneous angular velocity and is represented by omega. Angular velocity omega is defined as the rate of angular displacement and is measured in radians per second. Note that the angular velocity is a vector quantity. If the right hand's fingers are curled in the direction of the rotation of the body, the direction of the stretched thumb is the direction of the angular velocity omega. When a rigid body is in pure rotational motion, the angular velocity of each particle is the same and is equal to the angular velocity of the whole body. If the angular velocity of a rigid body changes with time, it is said to be moving with angular acceleration. The rate of change of angular velocity is defined as angular acceleration, alpha. Alpha is equal to d omega by dt. In the SI system, it is measured in radians per second squared. This is also a vector quantity and its direction is along the vector d omega, which represents the change in angular velocity. Now, let us consider an example. When switched on, a fan attains its maximum angular speed of 30 radians per second in 12 seconds. When switched off, it takes 120 seconds to come to rest. What is the angular acceleration of the fan in both cases? In the case of increasing angular velocity, we get the angular acceleration alpha 1 is equal to 2.5 radians per second squared. In this case, both angular velocity and angular acceleration are in the same direction. In the case of decreasing angular velocity, alpha 2 is equal to minus 0.25 radians per second squared. Here, the direction of angular acceleration is opposite to that of the direction of angular velocity. For a better understanding, let us compare the terms related to translational motion and rotational motion. Observe a rigid body rotating about a fixed axis with an angular speed omega. Let v be the linear speed of a particle p, that is, at a perpendicular distance r from the axis of rotation. When the rigid body is in rotational motion, if the length of the arc traversed by the particle in a small interval of time is s, then s is equal to theta into r. On differentiating with time, ds by dt is equal to d theta by dt into r. V is equal to omega into r. This is a useful relationship between linear and angular speeds of a body. In vector notation, we can represent the relationship between linear velocity v and angular velocity omega as v is equal to omega cross r. This is applicable to a rigid body rotating about a fixed axis, as well as to a rigid body rotating about a fixed point. You have now reached the end of this module. In this module, you learnt that when a rigid body is in pure rotational motion, the angular displacement of all the particles of a rigid body is the same and is equal to the angle through which the rigid body has rotated about the axis of rotation. In the SI system of units, angular displacement is measured in radian. The ratio of the angular displacement and time is defined as average angular velocity of the particle. Angular velocity is defined as the rate of angular displacement, omega, and is measured in radians per second. If the right hand's fingers are curled in the direction of the rotation of the body, the direction of the stretched thumb is the direction of the angular velocity, omega. The rate of change of angular velocity is defined as angular acceleration, alpha. We can represent the relationship between linear velocity v and angular velocity omega as v is equal to omega into r.